In this video we're going to talk about offsets, which are unbalanced currents or voltages in our amplifiers that are caused by asymmetries between two differential halves of the differential amplifier circuit. I've drawn an emitter-coupled pair here to kick off the discussion of offsets. It has slightly mismatched collector resistors, so the right resistor is a little bit bigger by an amount delta R. We're going to analyze the large signal effects of this mismatched component. We're skipping the small signal analysis of it because it's surprisingly complex. For example, it introduces another two gains called differential to common mode conversion gain and common mode to differential conversion gain. And as usual, we'll indicate we'll be sticking with large signal analysis by using large signal notation throughout, like VOM here. Fortunately, the large signal analysis is simplified by the fact that QP and QM are in forward active and delta R is a small value. That means the tail current still splits evenly between QP and QM because the collector voltage of a BJT in forward active doesn't appreciably affect the emitter current or the collector current. Knowing that, it's easy to calculate the two output voltages. Each is below VCC by the resistance times I tail over 2. That means these two voltages are different from one another, which is new. During our half-circuit analysis, we assumed that the halves of the circuit were identical, so that the output voltages were both equal to the common mode output voltage. This difference in output voltages has a special name. It's the output referred offset voltage. You find the output referred offset voltage by finding the difference between VOP and VOM when the inputs are equal to one another. Another common measure of offset in amplifiers is given by the input referred offset voltage. This is the voltage difference you'd need to apply at the input in order to make the output voltages equal. Put another way, it's the input differential mode required to cancel the output referred offset. Because delta R is small, the output offset is a small signal, and that means that you can calculate the input difference you'd need to use to cancel it by using the small signal differential voltage gain. So dividing the OOS by the differential mode voltage gain gives us our input offset, which is shown here. So a few notes. We're sort of ignoring that this offset voltage, this additional I tail over 2 times delta R, has created a common mode shift the output to. We're just pretending that it's purely differential mode, which we can get away with by saying that it's a small signal. But if we're being very persnickety, the output common mode is halfway between these VOP and VOM has this additional bit added to it. It's also worth noting there are all kinds of other offsets we could discuss in this circuit. So for instance, if QP and QM had different GM values, you'd have slightly different gains to the two different sides of the amplifier. If QP and QM have different beta values, then you'd have different currents that flow in through VIP and VIM. And if QP and QM have different IS values, then you'd get a small voltage offset from that. Manufacturing variation does cause all of these parameters to change, and managing these mismatches is a major task of circuit designers. So there are lots of neat tuning and canceling techniques that you learn about in the future. So in summary, mismatched elements create offset voltages or currents. We're analyzing large signal DC offsets. Output referred offsets are differences in voltage at the output of a differential amplifier. Input referred offsets are the differences in input voltage needed to cancel output referred offsets. And so you can find them as the offset voltage is equal to the output offset divided by the differential voltage gain, because the output offset is usually a small signal.